first equation and manipulate it and produce a different equation. The first equation is Vf equal to V0 plus At. I'm going to square both sides of this equation. Can you square both sides of this equation? Vf squared equal to V0 plus At all squared. Now, I hope you know how to expand a squared term like this. A plus B all squared is A squared plus 2AB plus B squared. Is that right? I think so. So how do you expand this? This will be square of V0, V0 squared plus 2 times V0 times 80, 2V0 80, plus the square of 80 is A squared T squared. Okay, now I'm going to factor out a 2A from these two terms. I think that will be a little difficult for you. Is that right? I don't know. I'm going to take these two terms and factor out a 2A. Now, you notice that there is a 2A here. There is an A there, but there is no 2 there. So how do I factor out a 2A from these two terms? Now, look what I'm going to do. I'm going to multiply that term by 2 and divide by 2. Does it make any difference? 2 divided by 2 is 1. Now what that did is, I can now factor out a 2A from there. So, when the 2A comes out, what is left in the first term? 2A has come out. What is left in the first term is V0t. And after this 2A, this is A squared. After 2A has come out, what is left here? There is a 1/2. You see that 2 in the denominator? This 2 has come out, leaving that 2 on the denominator. That will be a 1/2 At squared. Now, how beautifully we produce that quantity. When 2A is factored out from these two terms, what is left there is V0t in here plus 1/2 At squared in the next term. Okay. Now what has it achieved? Why did I do that? If you look at inside the parenthesis, what is this? V0t plus 1/2 At squared. This is the displacement x. So we can now replace this by the displacement x. So we have the third equation. What is that? Vf squared equal to V0 squared plus 2Ax. That is the third equation. I want you to write down these equations and learn them. The first equation is Vf equal to V0 plus At. That doesn't contain the displacement x. The second equation, x equal to x0 plus V0t plus 1/2 At squared. That equation does not contain the final velocity. And the third equation is Vf squared equal to V0 squared plus 2Ax. Tell me, what is missing in this equation? It's very important to know that. There is no time here. You see, the quantities you must be looking at is initial velocity, V0, final velocity, Vf, acceleration A, displacement x, and time t. There are 5 quantities. Each of these equations is missing one of them. Now, you should know that because when you want to solve a problem, which of these are you going to use? So this understanding is very important. Now, let's talk about acceleration of free fall. You see, all freely falling object, if I drop this ball, it falls to the ground, and as it keeps falling, it accelerates downward. All freely falling objects has a downward acceleration. Now, I told you some time ago that if you have a downward acceleration, we call it negative. Is that right? Now, what is the cause of this acceleration? The cause of this acceleration is the gravity. Earth is pulling it. And because of that, the speed will keep on increasing. And therefore, we say all objects fall with an acceleration called acceleration due to gravity. All falling objects have the same downward acceleration called the acceleration due to gravity, and we will represent that by the letter G. So, in place of A, when you want to deal with objects that are thrown up or down, that are subjected to this acceleration of gravity, we will replace our A by G. And this acceleration has been measured. What it says is that if I drop this object or this object or some other object, all these objects will actually fall with the same acceleration. All falling objects fall with the same acceleration, and that acceleration we call G, acceleration due to gravity. Its value has been measured as 9.8 meter per second squared. So any falling object has an acceleration of negative 9.8 meter per second squared. We use it negative because it is directed downward. Since the acceleration of a falling object is directed downward, we use negative G as the acceleration of free fall. Now, what is the acceleration of an object that is thrown vertically up? You see, the moment I throw this up, it begins to accelerate downward. That means whether an object is thrown up or simply dropped, both these objects have the same acceleration, the same downward acceleration, which is negative G. The moment the object is thrown up, it begins to fall freely with an acceleration negative G. There you are. You see, as the object is thrown up, the moment it is let go, it begins to fall back. And that is why it stops and then fall back. Its acceleration throughout the journey will be negative G. That's right. Its velocity while going up is positive, its acceleration is negative. So you must look at that. If when you throw an object up, while going up, its velocity is upward and its acceleration is downward because it is being pulled by the earth. So if the position of an object that is thrown up is y, the equations of motion. So because we are now dealing with vertical motion here, the position will no longer be called x, we will call it y. That means if you now want to construct equations for a freely falling object, we can use the same equations we developed earlier, but we will replace a there by negative g. So the first equation for a freely falling object is v sub f equal to v sub 0 minus gt. y equal to y0 plus v0t minus 1/2 gt squared. I hope you understand why I'm using y and not x. And what will be my third equation? Vf squared equal to v0 squared minus 2gy. Look at that, I forgot to change that a to g. It'll be minus 2gy. So these are the three equations for a freely falling object. What are the changes we made there? X has been replaced by y, and a has been replaced by negative g. Negative g is the acceleration of all falling objects. Okay, let's move on now. Let's do a small problem. An automobile moving with a velocity of 40 km/h along a straight road is braked uniformly to rest in 5 seconds. What is the average acceleration of the car during this time? Now, what are the information given to us here? An automobile moving with a velocity of 40 km/h. Now, first of all, you need to convert that km/h to meter per second. Do you remember the quickest way to do that? I have shown you in the first lesson. Km/h can be converted to meter per second by simply dividing by what number? 3.6. That's right. So this is your initial velocity when you start looking at it, when you start your clock. The automobile has a velocity of 40 km/h and it is braked uniformly to rest. What is the final velocity? It is brought to rest. The final velocity is 0. And this happened in a time 5 seconds. Let's write that down. V0, initial velocity, is 40 km/h. And that will be 40 divided by 3.6 meter per second. That is 11.1 meter per second. That is the initial velocity. What is Vf? Vf equal to 0. Alright, the time is 5 seconds. But all we need to do is to find the acceleration. We can either write down the equation for the acceleration right away or use the first equation. We can use the definition for acceleration. Acceleration is change in velocity, Vf minus V0 over time, and that will be 0 minus 11.1 meter per second divided by 5 seconds. That is negative 2.2 meter per second squared. Now, don't confuse the negative acceleration. I told you acceleration due to gravity is negative because it is directed downward. Now, this acceleration is negative not because it is directed downward, but why? Because this acceleration is directed opposite to the velocity. As the car is going forward, when you apply the brake, the acceleration will be backward. So the acceleration is negative, indicates that the direction of acceleration is opposite to the direction of displacement. Another problem. The driver of a pickup truck going 100 km/h applies the brakes, giving the truck a uniform acceleration of negative 6.5 meter per second squared while it travels 20 meters. What is the velocity of the truck at the end of this distance? What is the time taken to travel this 20 meters? Always look at